All right, welcome to lecture 4 of the course Agricultural and Biosystems Structures Engineering. This is the first topic on the different portions of a building or structure, and this will be on beams. And why is that? It's because it's the uh, nearest topic that aligns with the previous topics on stresses. And remember the formulae that were used. We have the normal stresses, eggshell stresses there, and then the shear, the bending, and the bearing. Now, beams are involving bending, horizontal shear, and bearing stresses. In the actual construction industry, where we have different materials involved, the beam would usually be wood, reinforced concrete, or simply just steel. Okay, the I beams that are called as they are. Now, focus will be first on the wood beams, and in the design, again, it's very important to economize the specifications of this the cross sections of this beams. Thus, okay, it is important to look into the modes of failure, or where at what kind of stress that the beams are going to fail. That's why, okay, let's go first to the design of rectangular beams. And in here, the first stress that is considered is bending. Again, three stresses that the beam is experiencing: bending, horizontal shear, and bearing. Imagine the beam, okay, carrying the load of the structure, even if it's just the roofing, but more so if you consider high-story buildings where you have the upper floors, okay, being carried by the beams. So you have here the first one, bending, and it simply is computed using what? The M, okay, the maximum M, okay, the moment, which is again determined using the bending moment diagram, okay, and it's divided by the S, which is the section modulus of the beam in MQ. Very direct, okay. Now, what is um, the sigma B prime on the right? Okay, that is the maximum allowable. Okay, the maximum allowable bending stress in pascals. Okay? So the M over S, okay, should be within that limit. Okay. Okay, so that is the first. This is very direct, so let's just leave it as that. Next one is we have horizontal shear stress, and this time, okay, the shear stress is this is a derived computation formula from the previous topic on shearing, shear stress. So you have here the actual horizontal shear stress as 3V over 2A, okay, or 3 halves of the V divided by A. And you have here the maximum design shear in the beam, okay. Later, there's going to be a topic on combined loadings. But so in here, we just talk about shear in the beam, okay. One-dimensional, or one along the plane, for example, that cross-sectional area. So that is a plane. And then you have your maximum horizontal shearing stress, okay. That should be the allowable, okay, the limit. Again, similar to the sigma B prime. Again, this is very direct. Just compute for the shear, okay, using your shear diagram from your loading. Okay, so you compute the reactions on the supports, and then you are able to generate the shear and bending moment diagrams. You find the shear. You're able to compute for this horizontal shear stress. You get the moment, you get the bending moment stress. Lastly is, okay, you have your bearing stress. And that is simply P over A. Okay, you still have your maximum allowable. Okay, and the P is the reaction force in terms of newtons, and then you have your contact or bearing area between beam and the support. That is in, again, the m squared, the usual m squared. All right, so very direct formulae, and once you have this values, one is able to solve, okay, directly at what kind or which the values for your bearing stresses, and at which um, values will they be failing. Now, the beams, okay, the wood beams are usually purchased from a store, okay, from a lumber store or a construction supply store, okay, in their in their um, commercially available standard dimensions or specs. So, okay, it is important to, once you are trying to compute for the dimensions of your beam, okay, you have to adjust to get, unless you're able to trim it down to the size that you need. But okay, at most times most times you would be using that commercially available dimensions, okay, or commercially available um, specs to uh, in use, okay, in your application. And thus there should be a computational adjustment, okay, with this design, okay, to fit the actual use. Now let's go to deflection, and well, this is the deflection of a wood beam. This is simply the deformation that accompanies the bending, okay, and it usually occurs at the center span of simple beams. The maximum beam deflection and then the allowable beam deflection, as shown, okay, they should be the maximum should be below the allowable. Now, there are differences in the reactions of uniformly distributed loads, uh, concentrated loads, and the structural members. And we'll be going through them one by one. Okay, let's start with the uniformly distributed load. Okay, take note of the diagram a while ago for the maximum deflection. Okay, this is a derived formula. Okay, but just a workaround of the different formulae used already or already available out there. Okay, so W is the uniformly distributed load, Newton per m, Newton per meter. You have the span length in meters, and then you have the modulus of elasticity of wood in newtons per m squared, and the moment inertia of the beam section. So the formula for the deflection, the maximum deflection of that is 5 over 384 times the quantity WL raised to the fourth all over the quantity all over E times I. Okay, this would give the maximum deflection, and the maximum deflection should be below the allowable. For concentrated loads, okay, the formula is 1 over 48 times the quantity PL times raised to the L raised to cube, and the quantity all over E times I. Okay. Similar in format, it's just the constant multiplier at the start of the equation. So for concentrated loads, you have these are for beams carrying two equal concentrated loads at the third points of the span. Okay, you have here 23 over 648 times P times L to the cube or L cube, and then all over EI. Now, for structural members, you have the roof member supporting plaster or floor member. Okay, so this is for live load only. You have your deflection, maximum deflection at L over 360, and with live load and dead loads, that becomes L over 240. Now, wood is done. Okay, we have now the reinforced concrete beams, and we have reinforced concrete beams because the concrete, while it is a very good and very cheap material in construction, its tensile strength is 0. Thus, it is important to reinforce the concrete with steel because the concrete actually meshes completely with or attaches completely to the steel, so that well, except for very short ones, okay, but in very long beams or very long lengths, okay, the beam is fixedly attached to the steel that it allows for the okay, cohesion of the two so that they move together, and the steel, okay, renders or gives its tensile properties to the concrete reinforced concrete beam. Well, the steel actually still the steel still carries the load of tensile strength, okay, all the while the concrete well, both the steel and the concrete are carrying the compression supposedly, but we'll see later on based on the geometric properties of the beam, okay, that we see the steel solely carrying the weight of the tension, and the concrete now carrying the compression. A balanced design for concrete beams is that we have the limiting stresses in the concrete and the reinforcing steel bars reached simultaneously, thus failing at the same time. An under-reinforced design has the steel reinforcement lesser than required, causing the steel bars to reach the limit stress. Before the concrete do, okay? Concrete remains under stress. And upon reaching the ultimate load, cracks appear. And lastly, of your over-reinforced design has the steel reinforcement greater than required, causing the concrete to be stressed compressively more than the steel bars in tension. And upon reaching ultimate load, failures occur suddenly without warning. What we want to avoid is letter C. And why? Because once you reach the ultimate load, okay, failure is suddenly happens without any warning, and that causes this dangers in construction. Okay, in most cases of accidents where buildings collapse without any sign, it's more important to focus on making a balanced design or even under enforce the structure, so that before the steel could reach ultimate load, the cracks already appear on the concrete, so that one is able, or the engineer is able to remedy the situation. So let's proceed with the geometry of reinforced concrete beams, and then we'll try to solve one in a while. Okay, so this is a schematic of the cross section of a reinforced concrete beam. You have here the gray portion as the concrete, and the black circular dots are actually the reinforcing reinforcing steel bars. Okay, and the dimensional geometries, the geometry of the drawing is provided. You have the width of the compression zone, the complete compression zone in meters as B. Okay, all right. You have B. Where is that? B is right. B is over here, and the height of the concrete beam is H, and D is the depth. Okay, the effective depth of the section. Okay, for stress analysis, because this is the centroid of the steel bars. Okay, then KD is the portion of the D from the top to the neutral axis. So this is now the neutral axis. Okay, should be familiar with this. You have your JD, which is the internal moment arm between T and C. Okay, what are these T and C? These are the tension and compression forces applied to the structure, okay, to the beam. The maximum compressive stress in the concrete is Newton per m squared, and you have the tensile stress in the steel bars Newton per m squared, and N. Introducing the word the letter N, which is the elastic ratio. Okay, this is the elastic ratio, which is simply the E. Okay, the modulus of elasticity of the steel over the modulus of elasticity of the concrete. Later, this will be very much useful in determining some values that would be, for example, in the dimensional lets or values of the geometry. Okay. Right. So let's proceed now to the relationships of this geometric parts of the drawing. Okay, so you have your, and this has already been given. You have this is the steel, okay, steel over the concrete, and the stress is my over I. This has already been provided. Okay, and you have your sigma 2 negative n times my over I. Usually this is for steel. Okay, okay, it's known. Okay, 2 is steel. Now you have here some equations that would prove helpful in the analysis and solution of for reinforced concrete beams. You have your P, the percentage of reinforcing, which is unitless, the AS, okay, the cross-sectional area of reinforcing bars, and all over the B and the D, okay, the width of the cross section over the height or the depth of the cross section. Then you have your moment CJD, okay, compression, okay, and simplifying it becomes 1/2 kJ FCBD squared. FCS, okay, the compression force is 2m over kjbd squared. The moment of the tension is as shown. The final the Fs is m over as jd. Let's try to solve this, okay, for a given example. Okay, but before we do, okay, here are also some relationships, okay, to show the values of the k, the j, and the p. Okay, you have the limit. This is we want to limit the tensile steel, okay, percentage to 0.75 of a ballast design to ensure that ductile failure occurs. Okay, and then there would be cracks, but it much better than just failing without warning. Okay, and we want for ballast design. For a ballast design, these are the values for your K, J, and P as shown. Okay, 1 over the quantity 1 plus f of s over n f c. J is 1 minus k over 3. And the P is FCK, the compression force times the K over all over 2 times the compression force of the steel. Okay. Okay, this is an example. Okay. But instead of having a rectangular or a parallelogram, we have a T-shaped uh, T-shaped beam. Okay, reinforced concrete beam. Here what we must ask is to find the largest allowable bending moment for beam if n. Okay, again the cross section is already given, so you have your n equals to the EST over ECO. Okay, the modulus of the CCTs of steel over concrete, which is 8, and then the working stresses are 12 megapascals and 140 megapascals respectively for concrete and steel. Let's move over to the all right, so we are here in Microsoft whiteboard, sorry. Now we have the beam, okay, as shown, and we want to solve for the maximum allowable bending moment. Okay, unfortunately, the beam, it does not have any portions of it, or the geometry of it identified, so we'll have to reconstruct that. Okay, you want to first find the neutral axis. What's that area? Okay, that should be the NA. And we want to compute for the other portions first. Okay, so you have your 5 reinforcing steel bars there. You have here, this is going to be 600. Okay, it's just millimeters, but let's just forgo the dimensions first so that it's simpler to write. Okay, you have your KD over here. Set the distance from the top to the neutral axis. And then this is going to be what? This is going to be KD minus 100. Okay, and this one, this is going to be 600 minus KD. Right. And well, you have your y-axis over here. Should be denoted as well. Now, we want to compute for the this is going to be A1, this is going to be A2, because we want to compute for the neutral axis, right? So we will be revolving this, no? We're going to get the moment of inertia, right? So what we have is we have this also as little area of 1, no. This is 2,400, right? So A3 is actually N times AST, as I was saying a while ago. The N proves to be useful. It's going to be 8, okay, as identified. 8 times the AST is 2,400. What is that? That is 2,400 millimeters squared. Okay, so this becomes 19,200 millimeters squared. We have to find A2 and A3, A1 and A2. Okay. Let's proceed with the solutions. Okay, so you have your 75 times 10 to the 3 millimeters squared times KD minus 50. Okay, A1. Let's try to to simplify this one. It's going to be 750 times 100. It's going to be 75 times 10 to the 3 millimeters squared. And you have your y is going to be kd minus 50 millimeters, and A2 is 400 times KD 400. Where's the 400? 400 times KD minus 100. Okay. Minus 100 millimeters. All right. So this is going to be m squared y. Again, this is the distance from the neutral axis. Okay. So you have kd minus 100 over 2, okay, millimeters. A3 is, again, we have already solved for that, 19,200 millimeters squared. And you have lastly your okay, last be your y3, which is negative 600 minus kd times okay. That completes the areas. So we try to solve for this one. Okay, it's going to be 75 times 10 to the 3 times 80 minus 50. Let's just set up the equation. Plus 400 times AD minus 100 over 2 squared minus 19.20 times 10 to the 3 times 600 minus KD. Okay, and we try to we supposedly there should be a zero moment, but the inner axis, it is fixed. So you have your equation, and simplifying it is going to become a quadratic equation, and the formula is going to give you the KD is going to be 155.55 millimeters. You'll try to solve for that one, okay? Because that would actually take a lot of time. Now, I, becomes what? And you have the KD already, so I becomes 750 times 155.55. This is going to be cube all over 3 minus 350 times 55.55 cube over 5 plus 19.2. Okay, times 10 to the 3 times 444.45. So you just simplify now. We have 600 minus 155 is going to be 444.45. Okay, so sorry, this should be going to be corrected. Well, this is going to be the I. Okay, it's going to be the I, and you get the I. Okay, solving is going to become 4.714 times 10 to the 6. Okay, times 10 to the 6 Newton meter, and this would be 4.714 times 10 to the negative 6 m. Oh, no, sorry, this I, and it's going to be in millimeters to the fourth. In meters, this is going to become 4.1 4 or 4.714 times 10 to the negative sixth m to the fourth. All right. So this is the final I, and we get now the moment. Okay, the moment is simply the allowable for the concrete. Okay, for the whole length times the I over the H. This again for the concrete. Okay, so you have your 12 times 10 to the sixth pascals. No, this megapascals times the I, which is 4714 times 10 to the negative sixth. Uh, hmm. Okay. Yeah, this is 4,700. So let's just correct this one so that this is corrected properly. And this would give a value of, and they still have to divide this by the H, which is 155. Oh, sorry, that's KD. KD. This is KD. 55.55 times 10 to the negative 3, which would give an M of 364 times 10 to the 3 Newton meter. Again, this is the final answer. No, because we still have to find for the steel, and the steel is going to fail based on its own allowable stress. Okay, this would give 140. Is it 140? Yeah, it's 140 megapascals. So times 10 to the sixth, and you have to multiply that with the same 4714 times 10 to the negative sixth meters to the fourth, and you have your n. Okay, you have to get your n. Sorry, it should be 1 over n. Okay, don't forget the n. You have to multiply that as well. So 8. That's 8. That's an unitless quantity. 444.45 times 10 to the negative 3. This would yield a value of 185.6 times 10 to the 3 Newton meter. We can see that we have this one, okay, bigger than the results of the steel. So we're going to make use of this value as our final, okay, our final moment, okay, because at this moment the beam is going to fade. So how what more will it be doing with 364 times 10 to the 3? Okay, so we have to choose this moment due to the steel. Let's proceed back to the slide, and let's have another example here. This is now for a steel beam. Now the steel beam is well, it's already available. I mean, the formula is already available based on the usual formula. Okay, used. Okay, you have your my over I, and it's a single material. Now, what is distinct between the steel beams is the geometry, because it's usually is shaped as an I. This is an I beam, okay, and in this case, okay, it's going to be a very long beam. Okay, often the design would be long enough so that the cross section of the eye is obviously like an extruded letter I, like that, right? So you have your Right, so that's going to be the edge. Let me just draw using the edge rather than doing it like that. So you have edge as looking an eye, okay? And then you have your structure, the middle portion as just a long bar, okay, from the edge to the other edge. All right, so we have here a 10-meter beam simply supported at its ends, okay, and carries a uniformly distributed load of 16 kilonewton per meter over the entire length. Okay, and what is being asked is the lightest W shape. Okay, because this actually is a W shape. That's the formal, okay, the formal term to refer to this kind of beam, steel beam. Okay, what is being asked is the lightest W shape beam given a limit of flexural stress, okay, or bending stress of 120 meters megapascals, okay, or 120 times 10 to the 6 pascals. And eventually, another question is, what is the actual stress in the beam? Okay, they'll have to use the diagram as shown. Okay, this is an ADSTM6 American wide branch beam, and okay, the dimensions of the beam or the specifications are provided. Why is this? Because these are actually manufactured or are as commercially available wide branch beams, okay? And it's because, okay, it's simpler to just buy what is commercially available than simply, okay, or customizing one, okay, for a specific use. So these are made readily available because this have already been computed as to their well, the properties of the material and also the dimensional integrity. Okay, so the table provides the designation for your commercially available wide branch beam. That's the first column. You have your S. Okay, the S is I over C, and it's times 10 to the 3 millimeters cubed. You have that value, and then the weight of the beam is also provided. So how do we solve for this one? Right, let's try to solve this problem. Okay, so you have a beam. Okay, let's try to see it from this cross section, from this so the side view. Okay, let's see the distributed load of 16 kilonewtons per meter, right? And this is going to be, well, there are going to be reactions at the ends. Let's denote it as F1 and F2. This is going to be 10 meters, right? From end to end. Now, the total load is going to be FT 16 kilonewtons per meter times 10 meters. We get 160 kilonewtons. Solving for the reactions on the ends due to the support. Okay, we have like that, and since we know that F1 is going to be F2, okay, so you have 2F1 equals 160 kilonewtons, and this becomes 80. Okay, F1 and F2 equals 80 kilonewtons. Right, and we want to solve for the bending moment. Okay, so you get first the shear. Okay, the shear is going to be, okay, draw the shear diagram. It's going to be from here. So it's going to be negative 80 here. Oh, 80, sorry, 80 kilonewtons. Going to go down at the bottom, and we get a, because it's going to be, we have a distributed load. Okay, so you have this negative 80, okay, kilonewtons. Now, to get the moment, bending moment, we just have to multiply this. Okay, this portion is actually 80 kilonewtons times 1/2. Okay? Why is that? This is going to be 5. This is the distance, okay, 5 meters. This is going to be the formula for the triangle. Okay, it's 1/2 base times height. Now we get the value for that. At the ends, there's going to be 0 moment, but at the center is going to be a maximum bending moment. Let's try to draw it correctly. Sorry for the beautiful drawing. The maximum, okay, is going to be at the center. And we know that this value is what? It's going to be this one. So 5 times 80 equals to 400 divided by 2 at 200 kilonewton meter. Okay? So this is going to be the maximum at 200 kilonewton meter. And we find for, we solve for S. Okay, the S is going to be 200 kilonewton meters all over 120 times 10 to the 6th Pascal. It's going to be Pascal Newton per m squared. Okay, so that it's Pascal, no? It's Pascal. So this is Newton per m squared, and we get 1.667, okay, 7 times 10 to the negative 3 m cube. This times 10 to the 3. That's why you have it times 10 to the negative 3 over here, right? Okay, so this is going to be in terms of mm cube. It's going to be 1.667 times 10 to the negative 3 meters times 1,000 millimeters over 1 meter, the quantity cube. So we get S 1,667 times 10 to the 3 millimeters cube. We look at the dimensional with the beam, the W flange beam, that the Y flange beam that accommodates this value of 1,667. So we try, or we see that we have your 460 times 89, which is at 1770. We have 167, so it's within. There's another one. It's 1690. Let's try to first okay, let's try to let's see if this already is enough, okay, to be able, okay, to well, to be able to carry the load, including the load of the the dead load. Okay, so because we have a value of the kilogram per m, or the weight, okay, of the beam, okay, on a per length basis. Okay, let's proceed. And we choose the W460. Okay. Use W460 times 89, which has a 1770 millimeter cube of S, okay, the mode section modulus, and 89.3 kilogram per m dead load. So we have the original distribution as something like this, right? On the beam at 16 kilonewton per m squared, and we are introducing a dead load. So that would introduce a weight of 89.3 kilogram per m, okay, per meter. This is going to be what? The equivalent of this one is times 9.81 meter per second squared, which would yield, okay, this is, yeah, 9.81 times 89.3. It's going to be 876, no? 876 newtons per meter, or 0.876 kilonewton per meter. So the total load is going to be, the load total is going to be 16.876 time. Okay, this is going to be kilonewton per m. Now we want to solve for the sigma f, or the flexural stress of this, the bending. So we have the weight as given, and what about the m? Okay, what's going to be the m? The moment is going to be 6. Okay, it's 16. Okay, 16. 16. Okay, 16. 16.876. Okay, we want to get the shear. Okay, the shear is simply what? Divided by 2, so you get, sorry, 16. You multiply it by 10, so it becomes, the shear max is going to be 168.76 over 2, which is 84.38 kilonewtons, while the M max is simply based on our diagram. Okay, so we have the formula, the F, or the V, times 5 over 2. So you have your V max times 5 over 2, which would yield, okay, it's 84.38 kilonewtons times 5 over 2 would yield 210.95. Now the sigma F, okay, or the flexural stress is going to be M max over S, and we get 210.95 kilonewton meter, would give us, okay, 1770 times 10 to the negative 3 m cube. So we get the cancellation of meters and the numerator. We get the value of 119.18. Is it within? Yes, it is. But okay, maybe there's a need to have some safety factor. So let's try to choose another, okay, another beam, beam design, beam choice, okay, choice of wide branch beam. So you use the we try to use the much smaller, okay, the much smaller 610 by 82. Okay. Oh, well, it's actually um, it's actually longer in terms of the the uh, 610. It's much bigger than 410, but it's smaller in terms of the flange. Okay, so we get the value 1870 times, and then the weight per length is 81.9. Please recall that so that uh, computation is simpler. So we get the values of uh, 1870 times 10 to the 3 mm cubed and 81.9 kilogram per meter. Again, it's methodical. We get the values 805. It's going to be 16. The total weight, okay, is going to be 16.803 kilonewton per meter. So it's going to be, it's actually lighter. It's actually lighter than our original. Okay, it's actually lighter. Okay, actually it's going lighter. That we're trying to find the lightest one. Okay. All right, so we have our V. Okay, the V is actually V max is 16.83. Okay, divided by 2 times 10 equals 803. Sorry. It's 1.803. It's 84.017 kilonewton per m squared. Oh, sorry. This is already, that's going to be the Vmax. So our Mmax is going to be 1/2 times 84.1017 times 5, which is actually 210.043. Notice the strike, no, the very small difference between the previous one, okay, for the beam, the other wide flange beam. Now we have our Mmax, and you just simply compute for the flexural stress, Mmax divided by the S. We have 210.042 over 1.870 times 10. Oh, 1,870, sorry. Oh no, yeah, it is going to be 1,870 times 10 to the negative 3 m cube. This is in Mmax is going to be kilonewton meter. Okay, we are going to cancel the m. So this becomes 112. Okay, divided by 1, we get times 10 to the 3. Okay, so we get 112.32 times 10 to the 6th pascals or megapascals. Okay, so we chose this one. Okay, this is already is lighter and you have a smaller flexural stress. In the next meeting, we're going to talk about columns. Okay. I'll be seeing you by 10. Thank you for listening.